Welcome to the Calculus Concepts course with me, Roman Kogan, as your instructor. Today we are going to talk about functions which comprise your toolbox in this course. The most popular kind of function which you will see often in applications are polynomials. These are just powers of x multiplied by some constants and summed together. For instance, 5x cubed plus 3x squared minus 7 is a polynomial of degree 3. Notice that the term of degree 1 is missing, which means that the coefficient of that term is 0. A special case of a polynomial is a linear function, which is one of the form ax plus b. Here, a is the slope and b is the y-intercept. If you draw the graph of this polynomial, it turns out to be, unsurprisingly, a line. Linear polynomials often pop up in models because they are simple and because a lot of things exhibit linear behavior. If you collect experimental data and the points kind of line up on a line, you can kind of guess what line that is by using a tool called linear regression. Another special case of a polynomial is the quadratic, that is, a polynomial equation of the form ax squared plus bx plus c. The graph of this polynomial is a parabola which happens to be a conic section, that is, a curve that you obtain by slicing a cone in a specific way. The Greeks were aware of such curves, and later on there were a lot of fruitful studies about them. However, these curves are interesting not because of cones, but because they model the path of a projectile, and by projectile I mean a bomb. The study of path of projectiles motivated a lot of mathematical research. This is probably the only positive side of people trying to kill other people with exquisite tools. Another special case of polynomial is just the n's power, f of x equals x to the n. Let's look at the graphs of these polynomials. So we have a line, a parabola, a cubic which goes down and then up, and then a degree 4 equation which looks kind of like a parabola but squished. Do you see the pattern here? The pattern here is the symmetry. When n is even, you can reflect the graph from left to right and it will stay the same. When n is odd, you can rotate the graph by 180 degrees around the origin and it will stay the same. Let's see why this happens. Consider the case when n is even, for instance x squared, and plug numbers in. 3 squared is, well, 9, and minus 3 squared is the same thing, so the right side of the graph looks exactly like the left side of the graph. Just reflect it. In general, this holds true for any even power, because minus 1 to an even power is just 1, so it goes away. In algebraic notation, this symmetry is recorded as f of x equals f of minus x. Now consider the case where n is odd, for instance x cubed. 2 cubed is 8, but minus 2 cubed is minus 8. Numbers with opposite signs will give results with opposite signs. In terms of the graph, that means that the values on the left and on the right are the same, except their signs are flipped. We can write down this symmetry algebraically as f of minus x equals f of x. This generalizes as well. The connection that you will discover now is that functions behave kind of like numbers. You have odd and even numbers. It makes sense to define odd and even functions to have the property that we discovered in the previous slide. That is, for odd functions, f of minus x is minus f of x, and for even functions, f of minus x is the same as f of x. So, with numbers you have 2 plus 3 equals 5, where 2 is even, 3 is odd, and the sum is odd. With functions, x squared is an even function, and x cubed is an odd function, because flipping the sign of the input flips the sign of the answer. Putting them together gives x to the fifth, which is an odd function as well. So even an odd put together is odd, which gives you a hint as to why they are called these names. Let's try something else. Put two odd numbers together and you get an even one. Put two odd functions together by multiplying them out and you get an even function again. It will be no surprise to you that as the sum of the even numbers is even, the product of two even functions is even as well. Notice here that we were summing numbers and we were multiplying functions. That's because the correspondence between numbers and functions that we are looking at here is not straightforward. The sum of numbers corresponds to the product of functions. With numbers, you could multiply them too. So an even number times an odd number is even. So for extra credit, try to figure out what that corresponds to with functions. That is, what do you have to do with an even and an odd function to get an even function out? In which way do you have to combine them to keep this correspondence? Let's look at more functions. X to the power 1 over n is a popular one. which is more familiar to you as the nth roots of x. And that's just the inverse of x to the n. Let's look at the graph. The graph of x to the power 1 over n is, unsurprisingly, just the graph of x to the n flipped over. Why? Well, consider the case of y equals x cubed. If y equals x cubed, then x equals y to the power 1/3. And if you label the graph on the left and squint a little bit, rotate your head, you will see that you already have the plot of x in terms of y. It's the same plot. So we can simply flip it across the diagonal to get the right plot. Now this trick won't quite work with the plot of x squared. Why? Well, let's draw it and flip it. Oh, now our graph will not pass the vertical line test if we keep both the upper and the lower part. That is, we will not get a function. That's because with squares, there are two numbers that square to the same thing. That's because x squared is an even function. So we keep only one of the branches, the upper one, to get the graph of the square root. More functions. Just like you have rational numbers, which are ratios of integers, you have rational functions, which are just ratios of polynomials. Same with algebraic. Algebraic functions are whatever you can get from polynomials by using plus, minus, times, divide, and nth root. For instance, x cubed minus 7 over the fifth root of x squared plus 1. Exponential functions are very popular and very useful because they model things like population growth, radioactive decay, and credit card debt. And logarithmic functions are just the inverse of exponential ones. Trigonometric functions, probably the student's most favorite kind. Things like sin x, cosine x, and tan x, they come from the ratios of sides of triangle, hence the name trigonometric. Trigon means triangle, but there is a better description, which I'll give in a different video. So why bother with all of this? That's because if you have real-world data, if you can figure out a function that approximates this data, you can build a model. And if you have a model, you can build predictions. And once you have predictions that are good, you're happy because you can predict the future, you can send satellites to space, and you can get science done. Now the time for the take-home question. Unlike numbers, the functions can be neither even nor odd. Your task is to find an example of such function and argue that your answer is correct. That's all, folks. Thanks for listening.